Have you ever stopped to wonder why things behave the way they do? Why does a ball, when released, always fall down? Or how a bike manages to stay upright, seemingly defying gravity, when you pedal and maintain momentum? It's not magic, not some mystical force, it's the elegant, predictable world of physics and math at work, constantly shaping our reality. Think of the universe as a giant, intricate puzzle, filled with countless interconnected pieces. And math? Math is the universal language, the key that unlocks the secrets and reveals the underlying rules governing everything around us. It's the code that makes sense of the cosmos. Every action, from the simple act of kicking a soccer ball across a field to the complex process of sending a text message across continents, is meticulously governed by these fundamental principles of physics and mathematics. They are the silent directors of our daily lives. When you kick a ball, sending it soaring through the air, you're instinctively calculating force, the precise angle of launch, and even the spin you impart, all without even realizing it. In that moment, you're essentially acting as a natural physicist, applying complex principles intuitively. Math then allows us to not only understand but also predict with accuracy where the ball will ultimately land, transforming these everyday actions into fascinating, real-world experiments. Even something as seemingly simple as walking is, in reality, a complex physics problem. One that your brain effortlessly solves automatically, constantly adjusting and adapting, meticulously calculating the necessary force, managing friction, and maintaining perfect balance with each step. These subjects aren't confined to the walls of classrooms. Instead, they represent the comprehensive instruction manual for navigating and understanding life itself. So, put on the special glasses of math and physics, shift your perspective, and watch as the world around you undergoes a profound transformation. Suddenly, you begin to perceive the hidden forces at play and the elegant, underlying patterns woven into the fabric of everything. This isn't merely about memorizing formulas or passing a test. It's about unlocking a powerful superpower. The ability to truly understand and make sense of the world around you, to see the invisible connections that bind everything together. Are you ready and eager to witness the universe's secret code come to life, to see math and physics in action all around you? Well then, let's get started on this incredible journey of discovery. Everything moves, from the smallest particles within us to the largest structures in the cosmos. It's a fundamental aspect of the universe we inhabit, from atoms to galaxies. And understanding this motion, its causes and effects, is the core of physics. It's about unraveling the secrets of how things interact and change over time. Physics studies this motion, seeking to quantify and explain it in a precise and consistent manner. It provides a framework for understanding everything from the trajectory of a baseball to the orbit of a planet. And math is its language. It's the tool we use to express these concepts, to make predictions, and to test our understanding of the physical world. Without math, physics would be a collection of observations rather than a powerful predictive science. We use speed, velocity, and acceleration as the fundamental building blocks to describe motion. These are the ABCs of physics, the first steps in understanding how things move around us. To describe how things move, they allow us to quantify not just how fast something is going but also its direction and how its motion is changing. Speed is distance over time, a simple yet powerful concept. It tells us how quickly an object is covering ground, regardless of its direction. Like biking 10 kilometers in an hour. It's a measure of how much distance you've covered in a given amount of time, a straightforward way to quantify movement. Velocity adds direction, transforming speed into a more complete description of motion. It's not just about how fast, but also you're going 50 kilometers per hour north. This tells us not only the rate of movement, but also the specific path being taken is different from just 50 kilometers per hour. The direction is crucial. It defines the vector and distinguishes it from mere speed. Direction matters. It's the key difference between velocity and speed, and it has profound implications in many real-world scenarios. A head-on collision depends on velocity, not just speed. The direction of impact is just as important as the speed at which the vehicles are traveling. Acceleration is any change in velocity, a concept that encompasses both changes in speed and changes in direction. It's the rate at which velocity changes over time. Speeding up, which we often think of as the primary example of acceleration. Slowing down, also known as deceleration, is simply acceleration in the opposite direction of motion, or turning. Even if your speed remains constant, changing direction means you are accelerating. Turning a corner in a car? You're experiencing acceleration even if the speedometer doesn't change. That sideways push you feel is acceleration, a result of the change in direction, constantly altering your velocity vector, even if your speed stays the same. This can be a counterintuitive concept, but it highlights the importance of direction in defining velocity and acceleration. Slowing down is also acceleration, a decrease in speed over time, and is often referred to as negative acceleration, just in the opposite direction. It's still a change in velocity, just one that reduces the magnitude of the velocity vector. On a skateboard, you can directly experience these concepts. Push to speed up, positive acceleration, increasing your velocity in the direction you're pushing. Coast, zero acceleration, maintaining a constant velocity unless acted upon by an external force. Drag your foot to slow down, negative acceleration, decreasing your velocity until you come to a stop. Or turn, directional acceleration. Changing your direction, even at a constant speed, is a form of acceleration. All these are wrapped up, neatly packaged into the single concept of acceleration. In one powerful concept, acceleration. It's a fundamental concept that allows us to understand and predict how motion changes over time. Math lets us calculate it, providing a precise way to quantify acceleration and its effects. Change in velocity divided by time. This simple equation is the key to unlocking a deeper understanding of motion. With these tools, we can describe, analyze, and predict the motion of objects with incredible accuracy, and predict motion precisely. From the smallest subatomic particles to the largest celestial bodies, the principles of physics apply. That's the language of physics, a language that allows us to understand the fundamental workings of the universe. It's a language of precision, prediction, and ultimately, understanding. Have you ever wondered why things move the way they do? Why a ball rolls down a hill, or why a car speeds up when you press the gas pedal? Why do things start moving in the first place? What makes them stop? And what causes them to change direction? These are fundamental questions about the nature of motion. Forces, those unseen pushes and pulls, are the answer to all of these questions. They are the fundamental interactions that govern the motion of everything around us. Gravity, for example, is a force that constantly pulls you down towards the earth. It's what keeps us grounded and prevents us from floating away. But at the same time, your chair is pushing you up with an equal and opposite force. This upward force counteracts gravity, preventing you from falling through the chair. When these forces are balanced, like when you're sitting still, you remain at rest. This state of equilibrium is crucial for stability. Forces, however, are not just about keeping things still. They drive change. They are the agents of motion. Nothing accelerates, speeds up, slows down, or changes direction without the influence of a force. It's the fundamental principle behind all changes in velocity. Imagine trying to push a heavy box across the floor. As you push, friction, that resistive force between surfaces, pushes back against you, opposing your motion. But if you apply enough force to overcome friction, the box will finally move. Friction isn't always a bad thing. In fact, it's essential for many everyday activities. Friction lets you grip a baseball bat securely, or it keeps your car safely on the road, preventing it from skidding out of control. Forces aren't just magnitudes, they also have direction. This makes them vectors, mathematical objects with both size and orientation. And thankfully, math provides us with the tools to add, subtract, and otherwise manipulate these vector quantities. When two people push an object together in the same direction, their forces add up, resulting in a larger combined force. But if they push from opposite sides, the forces can cancel each other out, leading to no net motion. The net force, the sum of all forces acting on an object, ultimately determines whether something moves or stays put. What about turning a car? As you steer, the road pushes your tires sideways, providing a centripetal force, a force directed towards the center of the curve, and this force is what causes you to turn and follow the curve of the road. However, if you lose friction like when driving on ice, you lose the ability to generate that centripetal force and you slide straight ahead, unable to turn. So every change in motion we observe, from the grand orbits of planets to the simple up and down motion of a yo-yo, is ultimately governed by these invisible pushes and pulls we call forces. And with the power of mathematics, we can not only measure these forces but also predict their effects on the world around us. Forces are the fundamental engines that drive the universe, shaping everything from the smallest particles to the largest galaxies. And that, in essence, is the unseen push and pull that governs our physical world. Forces cause acceleration, but how much? Newton's second law gives us the answer, F equals sign ma. F is net force, m is mass, how much stuff, and a is acceleration. More mass means more resistance to acceleration. Think bowling ball versus tennis ball. Push two shopping carts, one empty, one full, same force, but the heavy cart accelerates less. To accelerate a heavier object as much as a lighter one, you need more force. F equals sign ma lets us calculate exactly how much force is needed. This equation governs everything from a leaf in the wind to a rocket launch. Engineers use it to design engines, bridges, and more. It explains why a pitcher must throw hard to accelerate a baseball. F equals sign ma is simple, powerful, and everywhere. It's the mathematical link between force and motion. That's Newton's genius. Gravity is the force pulling everything together, keeping you on Earth, the moon in orbit, and planets circling the sun. Earth's gravity is strong because it's massive, that's why we notice it. On Earth, gravity accelerates all objects downward at about 9.8 meters per second squared. Drop a rock or a feather ignoring air resistance, and both accelerate at the same rate. Newton's second law gives us weight equals sign mxg, mass times gravity. Your mass stays the same everywhere, but your weight changes with gravity. On the moon, you'd weigh much less. Throw a ball, your hand gives it forward speed, gravity pulls it down, and together they create a perfect arc. Math lets us predict exactly where and when it will land. Gravity shapes every motion on Earth and beyond. What goes up must come down, predictably. Physics is also about space and shape. Enter geometry and the Pythagorean theorem. For any right triangle, a2 plus b2 equals sine c2. It's not just for math class, it's everywhere. Want a shortcut across a park? The diagonal is shorter and Pythagoras tells you exactly how much. Displacement, the straight line distance from start to finish, is found with this theorem. It's crucial for vectors like force and velocity. A plane flying east with a north wind, its true path is the diagonal, calculated with Pythagoras. Riding a bike up a ramp? The ramp is the hypotenuse. Its length, height, and steepness are all related. Engineers use these principles to design ramps, rockets, and more. Geometry turns abstract math into real-world solutions. The Pythagorean theorem is a bridge between math and motion. It's how we measure, move, and build. That's Pythagoras on a bike. Energy is the universe's currency, the ability to do work. It comes in many forms: chemical, electrical, thermal, and especially kinetic energy of motion. Kinetic energy, Ke equals sign 1/2 mv2. More mass or speed means more energy. Double the mass, double the energy. Double the speed, quadruple the energy. That's why speeding cars are so dangerous. Their energy increases fast. Stopping distance grows with the square of speed. Potential energy is stored energy, like a book on a shelf. Lift it higher, it stores more energy. Drop it, and that potential turns into kinetic as it falls. At the top, all potential. Just before hitting the ground, almost all kinetic. Energy constantly transforms from one form to another. This principle governs everything from falling apples to roller coasters. Math lets us track and predict these changes. Energy is the fuel for everything. Your smartphone is a marvel of math and physics in action. GPS uses satellites, orbiting thanks to Newton's laws and triangulation, a 3D Pythagorean theorem, to find your location. The touchscreen senses your finger by measuring changes in an electric field. Math turns those signals into precise coordinates. The display uses physics to control light, creating images pixel by pixel. The accelerometer measures acceleration, flipping your screen as you turn it. Communication? Your phone sends and receives electromagnetic waves, energy traveling at light speed. Math encodes and decodes your messages, filtering noise and correcting errors. Every text, call, or video is a symphony of physics and math. Your phone is a pocket-sized laboratory, proof that science shapes our world. That's applied science, right in your hand. Why care about F equals sign ma or the Pythagorean theorem? Because math and physics teach you how to think. They train you to break down problems, find solutions, and think critically. Skills valuable in any field. Solving physics problems builds your brain's problem-solving muscles. This process is used by detectives, doctors, and business leaders alike. Math and physics build resilience and confidence. For many top careers, renewable energy, AI, game design, robotics, medicine, these subjects are essential. They let you appreciate the world's wonders from rainbows to skyscrapers. Science replaces magic with elegant reality and empowers you as a citizen. Don't see these subjects as hurdles. See them as keys to understanding your universe. Embrace them, and unlock a richer, more powerful way to see the world. Your future is powered by science.